Hello and welcome back to Educator.com and welcome back to Physical Chemistry. So we've just finished discussing the idea of a particle in a box, and we've taken a look at some basic quantum mechanical systems, and we've taken a look at some of the properties and integrals and things like that. So in the next couple of lessons, what I'm going to do is I'm going to actually formalize what it is that we discussed in the last few lessons. So we're going to talk about the postulates and principles of quantum mechanics. Let's just jump right on in. So when we talk about a postulate, you can also call it an axiom if you will. What we're doing is we're taking a look at this entire body of data and we're saying, okay, let's take a look at this, how successful it's been, and instead of developing it one way, this idea of quantum mechanics, let's just begin with some postulates that are confirmed by a whole many years of data, and we'll use that as our starting point. For a first course in quantum mechanics, that's actually the best way to go. So I wouldn't really read any more into that. This is just sort of the formality of quantum mechanics. We lay these out as a bunch of axioms, just like when you study geometry. There was the axiom of parallel lines. There was the axiom of the shortest distance between 2 points is a straight line. Certain things that we need in order to develop the rest of the theory. So these are going to be the postulates of quantum mechanics. Okay. So postulate number one, the state of a quantum mechanical system is completely determined by its wave function, also called the state function. Just like the PV equals nRT, we call it an equation of state. So psi is the wave function, but it's an equation of state. It tells us what state the quantum mechanical system happens to be in. This wave function is a function of the particle's coordinates. So if we're talking about a particle in a one-dimensional box, it's going to be a function of x. A particle in a two-dimensional box, it's xy. A three-dimensional box, xyz, and so on. So however many coordinates, if you're talking about a five-space quantum mechanical system, you know, who knows? It's going to be xyz, something like that. All information about the system can be extracted from psi. This is very important. Okay. All the information that we need about a system can be extracted from psi. Okay. Now, psi star, psi conjugate times psi dx dy dz is the probability that the particle will be found in a differential volume element located at the point xyz. We've seen this before. Remember when we said that psi conjugate times psi, we call this, when we multiply these functions together, we get something called the probability density. When we multiply the probability density times either a length or an area or a volume, we get the probability. That's what this is. So this dx dy dz, that's just a differential volume element. At a given point, xyz, let's just say in the center of the box, well, this dx dy, I'm sorry, I'll do dy here, and then dz here. This is just a differential cube. So it's the probability that the particle will be found in that particular little region in space, or in the interval, or in the square, whatever it happens to be. So once again, psi star times psi times dx dy dz is the probability that the particle will be found in a differential volume element, dx dy dz, located at that particular point, xyz. Okay, and again, a lot of this will make sense when we start doing the problems. So again, a lot of these lessons are going to be a lot of theoretical discussion. We're going to lay out the theory, and then we're going to do the problems in one big swoop. So, okay, so let's see what we've got. So this thing that we just wrote, this psi star c dx dy dz will often be written this way, and I'll often do it this way. We'll just call it dv, a differential volume element. So this dv and the dx dy dz, they are the same. That's it. This is just the theoretical description. Differential volume element, dx dy dz, when we actually have to integrate this function, we integrate one variable at a time with respect to x, with respect to y, with respect to z. So when we integrate this, it's going to be a triple integral. If we had a dx dy, it's going to be a double integral. So we break them down into the individual coordinates when we have to run a calculation. Okay, so the two-dimensional version is going to be So just for completeness, the 2D version is this, and we do dA, where dA is a differential area element, and that's equal to dx dy. That's it. That's all that's going on here. A little differential area element where this is dx and this is dy if we happen to be talking about 2 dimensions. And of course the one-dimensional case. So the one-dimensional case, well, we've already seen several times. Well, we've actually seen all of them. This is just dx. That's it, where dx is some differential length element. Okay, now because this C star, psi, is a probability density, or if you want to just refer to it as a probability, that's fine. Okay, as a mathematical function, okay, let's just say as a math function. As a math function, it must satisfy the following properties. Must satisfy the following properties. So we are dealing with mathematical functions here, and certain things have to be the case. So the first one, the integral of this psi star psi dv has to equal 1 when we integrate it over the entire space that we happen to be concerned about. If it's some 3-dimensional box that is length 1 by 2 by 3, well, that entire space is integrating from 0 to 1 on the x-coordinate, 0 to 2 on the y-coordinate, 0 to 3 on the z-coordinate, our entire space. When we integrate that, it has to satisfy that the integral of this thing is equal to 1. And here's why. So we said that this thing right here is the probability of finding it in a particular differential element. Well, if I'm integrating over the entire space, I know that I'm going to find it somewhere in that space. I know that. So because I am 100% sure that I'm going to find it somewhere in that space, when I add up all the probabilities, it's going to end up being 1, which is the same as 100%, or 1.00. So when you find a probability, you're always going to get some decimal, which is going to be less than 1. When you add up all the probabilities for a particular situation, you're going to get 1. So that's all this means. Since this is a probability, integrating all the probabilities gives you 1. This is called the normalization condition. So this is the case because the probability of finding the particle somewhere in our region of interest is 100%, or 1.00. That's all that means. Okay, so a little bit of a notation here. When we're discussing theory, we're going to use a single integral as the symbol. Now, of course, this is a differential volume element, which means dx, dy, dz. In practice, again, that's going to be a triple integral. So, but in theory, when we're just discussing the theory of this, we're just going to use a single integral symbol. So I hope that doesn't bother you. All right. So let me just write that down. When discussing theory, we will use a single integral symbol. Okay, now, so in 3 dimensions, it's actually going to look like this thing will look like this. You're going to have psi star, which is a function of x, y, z, times c, which is a function of x, y, z, times dx, dy, dz is equal to 1. So this thing in 3 dimensions actually is this thing. That's all we're saying. Okay. Now,